true for all experiments. So we will have rate, which depends on observed rate constant, and this is multiplied by the concentration of A to the N. Okay. And what is K obst? That is correct. So that is K times the initial concentration to the order that it belongs to B. So we are extracting that from these experiments. So usually what we will have are data of concentration against time. So you will have these data to analyze, to plot, and to fit in order to determine both whatever would be the observed constant and your order of reaction, of pseudo order. Okay. In this case, we have as information half-life time. Okay. So we have this much of information, and this depends on what? On the order of the reaction. Exactly. If I see half-life times, then I can make an inference on what would be the order. No? So what we have seen is that T1/2 is proportional to the concentration of A to 1 minus N. And we can do this because we are isolating P so far. So we are analyzing a situation in which the behavior is this. So we don't look at this data, but we look at this concentration, only A. So going from experiment 1 to experiment 2, we are increasing A. What is happening with T1/2? It's decreasing. So we have an inverse order relation, don't we?
Yeah.
So N must be larger than 1. That much we can know. Could be 2, or could be 1.5, or could be 2.5, but it has to be larger than 1. So we discard that N might be 1, and has to be larger than 1. Okay. So what we have done to analyze this, and this is what we can do with two sets of data. We have two concentrations and two half-life times, is write this as the ratio between two natural logarithms of first the T1 halves for experiment 1 and 2, and this will be equal to 1 minus N,
the log of
the initial concentrations in the experiment 1 and the experiment 2. Why can we do this? Because these concentrations are the same. So the K observed must be the same. Okay. Only under that condition is that we can do this. Therefore, 1 minus N should be the natural logarithm of the ratio between these two half-life times over the natural logarithm of the ratio of concentrations of A for experiments 1 and 2. Okay, so how much is this? So we have for the first case 37 seconds divided over 13.9 seconds, and this is the natural logarithm of the concentrations for these two experiments, which are 0.3 millimolar divided over 0.8 millimolar. We don't need to make changes in concentration units because we are dividing the same units. So no need to write this times 10 to the minus 3 molar. And how much is this?
91.
Excuse me? Minus 1. Are you getting that from your calculators? Nobody is telling you? You are making sure that this minus 1?
Yeah, because it was over 2, so yeah. Oh, it's minus 1.
Okay. So do the calculation. Okay. So you have to make sure that you are understanding whatever I'm saying here, okay?
Yeah, I know.
And I'm expecting you to do the work seriously.
It was 0.99.
Okay, that's what I want to hear. I want to hear the actual number. You will have some error here. This is not something that comes straight out from calculation. So this is close to minus 1, and therefore we come to the conclusion that n has to be 2. And this is a second order. Okay? So this is one way of making sure that you are getting the right answer. Another way of coming to that conclusion is T1 half in terms of second order reaction. Javier, how much is it for second order?
It's
1 over
K
times
the concentration.
okay. So this will be 1 K observed times initial concentration of A. From experiments 1 and 2, we know that the K is the same. So this means that the product between the initial concentration times T1 half should be, this will be 1 over K observed. So it's a constant. How much is, if you please calculate, 0.3 times 37?
11.1.
Is 0 times T1 half, and we are doing this, and that is
11.1.
11.1. This is millimolar seconds. How much is for the second?
11.12.
11.12. So we have, either way you do this, you have to make sure that you are doing the right guess. So second order. Okay. Good. So now, from this, we should calculate which data, which information do we need. K observed. So we said it's going to be the same for these first two experiments. Okay? Please calculate K observed. How much is that? We can use either of these two because we are making sure that the values are equivalent, and therefore, and I have it from here, we come to the conclusion that K observed is 1 over A0 T1 half. And this is, let's write this for the first experiment, 0.3. Now I have to write this as 10 to the minus 3 molar times T1 half is 37 seconds for the first experiment. How much is that?
9.
Excuse me?
9.
Is this 9?
Yes.
Just 9?
9.00.
0.00 molar minus 1, seconds minus 1. Okay, good. So that is K observed for either first or second experiment. Is that right?
It's
90.0.
That's why I'm asking you to do the calculations. How much is it?
90.09.
Okay. Molar minus 1. Make sure that you are doing the right calculations. So that we will take as our first constant, observed or apparent constant. Now, let's get a second constant out from the third experiment. Now, this will be a different constant because we have a different initial concentration for B. So I'll call it K observed, and this is going to be the same for a different initial concentration of B, and this is 1 over 0.8 millimolar times 10 to the minus 3. The time for this is 21.8 seconds. And how much is that?
57.
57 point?
34.
34, thank you. Molar minus 1, seconds minus 1. Okay, so in this experiment, we have a different constant because we have a different initial concentration of B. Good. Now from here, and I think we have not written this, our K observed, I have it somewhere, is K over B initial M. Once again, we have two unknowns, and we need two equations to get to this information. As similar to what we have done previously for N, it comes to the equation that M is the ratio between the observed constants in these two experiments divided over the natural logarithm of the concentrations, initial concentrations of experiment. I think we can, yeah, we have only two concentrations, is 0.5 for the first one and 0.8 for the third one. So that's what we're going to use. So this is natural logarithm of, where are my values? 90.09 molar minus 1 seconds minus 1 over 57.34 molar minus 1 seconds minus 1 divided by natural logarithm of initial concentrations for B, 500 millimolar, 800 millimolar. And how much is that? How much is it?
Minus 0.96.
Minus 0.96.
Something's am I doing something wrong here? So this is fine. And this is okay, yeah. Nice. So this is minus 96. So this is minus 1. So we have a rate constant which is larger when our concentration of B is smaller. And that's why, yeah. So higher concentration of B, higher concentration of B, smaller K. So B is acting as an inhibitor. And then M is a minus 1. And therefore, with this, we come to the conclusion that V should be K times A squared over B. How much is K? So we have to get K out of this equation. Let's take one of these. K will be K observed
Over B.
B
No, times B.
0 M, which is K observed
Times B.
times C. Okay, let's do that. And this is K observed 9.09 molar minus 1 seconds minus 1 times
500 millimolar.
0.5
5 molar.
molar. And we get K out of this, and K is
45.045.
4, and this is molar minus, actually is,
Teacher,
yes,
also we could calculate if we have the observed from the first experiment, we can multiply it by the initial concentration.
excuse me,
If we have the observed constant, we can just multiply by the initial concentration? Or?
Yes, of course. Experiment 1 and experiment 2 have the same concentration, which is 0.5. Okay. So the units for K are seconds minus 1 because total order is 1. 2 over 1. Okay, so that is the kinetics for this reaction. Okay. Good. So let me work out second problem. In the second problem, we have data for rate constants that depend on temperature. What is the equation that relates these kinetic parameters? So we have Arrhenius equation that tells us that the temperature dependence of the rate constant is a pre-exponential factor e to the EA over RT. Okay, so there we go. So usually what we will have is information on different kinetic experiments performed at different temperatures. And what we will observe almost always will be that as we increase temperature, the rate of the reaction will increase. Almost always. There are some cases in which by increasing temperature we actually reduce the rate of the reaction. And these have to do usually with catalytic reactions, both heterogeneous, which depend on the absorption of our substance on the surface, or enzymatic, because enzymes have a certain range of temperatures at which they are efficient. At higher temperature, we will have denaturation, thermal denaturation, so we don't have efficient enzymes. So in those cases, there are some other reasons why the rate of the reaction may go down as we go high in temperature. But the norm is that always this will increase, and therefore, and this is something that you have to remember, the activation energy is a positive number. Okay? Good. Okay, so what we do is we linearize this equation. The natural logarithm of K is the natural logarithm of A minus EA over R times 1 over T. So from the slope, we can calculate the activation energy, and from the intercept, we can calculate the value A. Let's do this for two experiments. In this particular case, these data are calculated from an equation, so there is no dispersion in this data. And if you did a regression of your data, you might have found that the R square is 1. Okay? Because R square will be 1 when all our points are falling on top of the equation of a line. So we can take just two data and calculate the slope from these two values. So the difference between these two will be the natural logarithm of K1 over K2, and this is minus EA over R, 1 over T minus 1 over T2. So our activation energy is minus R, the ratio between K1 over K2, divided by the difference in temperatures inverse. Okay. So this is typical of an activated process. So when we have an activated process, we usually will have this form. We have seen this in thermodynamics, is the Banhoff relation of enthalpies with how enthalpies or equilibrium constants change with temperature. And actually, the Arrhenius equation is derived from the Banhoff relation because we have to comply with the thermodynamics. Okay? So what we do is just to select 2 points out of this set of data, and let's take the first and the last. And if you could please calculate that, either doing the regression or linear regression or any other 2 points. So this will be minus 8.314 joules mole Kelvin times the natural logarithm. And one thing that is not crucial in calculating the activation energy. Javier, leave the room, please.
No, I was just screaming.
Just leave the room.
I was screaming.
I'm asking you, please, leave the room.
It's 60. Oh.
Leave the room.
Okay.
Thank you. I don't appreciate that you are being clowning around here.
I'm
So
not telling you.
go outside.
So very expressive person.
So what we have here, and we have to be careful with, is the scale of our values. So we have to notice that sometimes these values will be factorized. And this is the case with the 10 to the minus 2 seconds minus 1. Okay? So this number will not be a crucial factor in determining our slope, because this number we will cancel out when we are dividing k1 over k2. So you might come with the right answer for the slope. But there is a problem when we are going to calculate a, okay? Because that will be the order of our pre-exponential parameter. So in this case, I'm taking these two values. Let's take this first. That will be 482 seconds minus 1 divided over, and see, minus 10 to the minus 2, excuse me, seconds minus 1, 1.06 times 10 to the minus 2, seconds minus 1, and divided over the difference between the temperatures inverse. So this is 361 Kelvin over 1 over 285 K. What are the units of activation energy? Joules per mole or kilojoules per mole. Okay? So this has no units. This has units of Kelvin, inverse, and this will multiply once that we take the inverse. How much is this value? If you could please calculate that for me.
64,898 joules over.
What was the number?
64,000.
64?
Yeah, 64,898.
It's a linear regression.
How much?
And that's 68.
68,000.
I think it's 68. I think that would be the closer value. 68?
1,877.
177. Okay. So yeah, it's closer to that, and we want to express this in kilojoules per mole, and we will usually not use as many significant figures. We have to look at our data and see how many significant figures we are using. We are using 3, and therefore this will be 68.9 kilojoules per mole. Okay? So always limit the amount of information to the one that you have to start with. And that is true for the measured information. So what we measure, of course, or we set in an experiment is the temperature, we determine the K. That is not the case for constants. Okay? Well, in this case, I use 8.314, but if you have much more, many decimals for your constant, R or whatever constant you're using, you can use as many decimals as you may. Okay? Good. So that is the activation energy, and what is left for us is to calculate the pre-exponential factor. I will erase this and be left with this equation, because from this we can calculate the intercept. And here we will have, I will just bring this value here and the K here, and of course since I'm moving, that will be equivalent to that.
The logarithm is negative, no? Of k. Or
This was subtracting from here, and now I've moved this.
okay.
Yep. So it's basically just moving this here.
Yeah.
And now we will know this, and we will know this much. Okay, so select any point. Let's select for this case the intermediate data that we have here. This is natural logarithm of, and here is the time that we have to be very careful with this 10 to the minus 2 seconds minus 1. This will make the difference between correct value or an incorrect value. And now I can use this in units of joules per mole, Kelvin, excuse me, joules per mole. And R is 8.314 joules mole Kelvin. And this is multiplied by the inverse of the temperature that we have selected, which is 304. And how much is our natural logarithm of A?
24.52.
24.52. So here we can also have as many decimals that we may have from the calculator, because we are not going to report the natural logarithm of A, but the value of A. Okay? So here we don't have units, but for A, which are the units? Same as the constant. That is correct. Same as the constant. Okay? So finally, A is E to 24.52. And how much is that?
4.46 times 10 to the 10.
10 to the 10 seconds minus 1. So that is our pre-exponential factor. This is telling me how fast the reaction would go if I'm at infinite temperature. If I go, there is no limitation. There is no kinetic barrier. That would be the rate. Okay? And this is telling me what might be limiting my reaction, for example. And is a number that usually relates to the order. If you look at pre-exponential factors for different orders of reaction, first order, second order, and so on, you will have different values which are characteristic. Okay? Also will have to do with if the reaction is occurring in solution, or if it is occurring in solid state, or if it is occurring in gaseous state. It will depend on how fast the reactions can move and how fast the reaction can occur. Okay? Good. So I think with that we have covered a very significant kinetic analysis. So we can determine the rate of the reactions, describe that in terms of K and orders, depending or independent of the complexity of the reaction. And we can also bring this same information to different temperatures. And then being able to select at which temperature would be the most convenient kinetically to do my reaction. Okay? I might want to make my reaction faster, or either faster or slower. So I can control that by controlling temperature. And we can, from the information of the rate constant or the rate law, we can control the kinetics of the reaction by changing what? Concentration. Exactly, concentration. So basically you have all what you need to know for making a kinetic control. Okay. So what we are going to discuss now is how the reactions may actually occur. Probably 90% of the reactions that we are going to study are not occurring as we have described. One simple step. But we need to describe them in reaction schemes, which means more than one step. So we are going to describe the simplest cases, okay? And this will be reversible reaction. A reaction that can go in one direction and come back. And we will need to use two rate constants in order to describe this. How fast is A forming B, but how fast B is returning back to A. Okay? So that is a reversible reaction. Okay? We will have the possibility of a sequential reaction. Now, the case is A goes to B, but now B can go to C in a second reaction. That is what we call a sequential. And the third variant is parallel
La segunda.
reaction. So A goes to B or A goes to C. Each step that we are going to analyze will have, of course, its own rate constant. Now, for sake of our study, we will assume that all these reactions are order 1, first order. But that may not be the case. This could be second or 0 order or whatever order this might be. And these are the simplest. Okay? Now imagine that we have the following situation. We have A that goes to B, and this goes to C, and this reversibly goes to D, and this follows so becomes complicated, but you see you can start composing this path. Imagine that closes like this. Now, when you are studying Krebs cycle, for example, in biochemistry, basically what you are looking at is, and in this case it's a cycle, but you are looking at a reaction that is a sequence of reactions. Okay? So you start with some transformation and you start changing the number of carbons of the molecule. And this is something that has to be occurring once and once again. That's why it's a cycle. But we could have transformations that are very complex in nature. And that's what we want to understand. Yes?
The use of K can be, well, the K can be used to calculate the percentage of a
Exactly.
molecule that we have.
Exactly. That will be our purpose. Because you will have to look at this, and probably your target is E. Get E. That is your product. Not F, not C. So how do you make your kinetic control to avoid your raw material to go to C and actually end up here and do not decompose to F? Okay? So you need kinetic control to do that. So we will try to discuss this in a very qualitative manner, but we will be able to deal this in a very quantitative, analytical manner. Okay? So let's start with the simple. So, reversible reaction. In order to actually describe the reaction, what we will do is we are going to describe any single step kinetically. Okay? So, this means for reversible reaction, what is the first step? A goes to B. So this means the concentration of A with respect to time changes and actually diminishes accordingly to
Increasing concentration of B.
K1 times A. So that is how A is going down. It's being consumed. Depends on how much I have of concentration of A and what is the value of K1. But that's not the only step involving A. There's a second one. The reverse one. And what is the reverse process doing? Increasing the concentration. So it's going in the opposite direction. It's a minus. It's not decreasing, but increasing. Depends on what? Concentration of B and K minus 1. Okay? So that is the equation that I have to solve. Now, in principle, you would say we have to describe A and B, but how is the concentration of B in time? Can you tell me that? At any time, how much is the concentration of B? I'm asking for you to tell me in terms of something that we know or we might know. Has to do with the initial concentration of A minus the concentration of A. Do you agree? Because that is the stoichiometry. If I have something of the initial concentration of A, and let's imagine nothing of B, as some fraction of A decomposes, B will be formed. Okay? So, from here comes, sorry that I don't have much space, that the concentration of A is just A0 minus X, and the concentration of B is X. And by arranging these two equations, I come to this conclusion. So the question is, how many independent species do I have in that first? Independent. Just one. Because the concentration of B depends on A. Okay? It's like in equations. I have one dependent variable and one independent variable. Well, actually two, because time is also independent. Okay? So this means that this equation I could rewrite only in terms of A. So this will be K1 times A, which is a function of time, of course, minus K minus 1, A0 minus A. And this is K1, and you see I'm having minus, minus, plus, so I can factorize K1 and K minus 1 times the concentration of A minus K1 A0. Javier, how do I solve that equation? How do we go for calculating or solving that differential equation?
We need to put all the terms that depend on A and separate it.
We can separate this because this it depends only on constants and A. So we can do variable separation. So this will be, and we are starting now to solve this. This will be, excuse me, K1 plus K minus 1 A minus K1 A0, which is a constant. And this will be just the T. So we are bringing this as a denominator, and whatever left here is multiplied by dt. So we are separating variables, and now we integrate this. Okay. Now I will probably bring this. I prefer that to have it on the other side, that negative. Now we integrate. What are the limits for time?
From
0 to t. Limits for concentration. Initial concentration of A to a time-dependent concentration. There we go. Okay. Let me turn off. If you could go ahead, please, and work the solution for that integral. What is the integral in general terms? It's a natural logarithm, but we have to complete our because we have to multiply this exactly. Let me do that. My variable is A, which I have in the differential, but I have it multiplied by a term here that I will complete. But since I am multiplying it here to make my variable complete, I have to compensate it by dividing outside. And that's just going to be the natural logarithm of whatever this number is. No? So that is 1 over k1 plus k minus 1 natural logarithm of k1 plus k minus 1 a minus k1 is 0 that I have to evaluate from a0 to a, and from the other side just minus 2. Okay, so moving forward, what I'm going to do is this factor that is dividing, I will move it to the right. This is k1 plus k minus 1 t with a negative sign in front. And now we evaluate, and since we have a natural logarithm, the difference is numerator and denominator. Yes?
The k that is with the initial concentration shouldn't be k minus 1?
You're right. Yes, and that's a good catch. Otherwise we could have significant problems. Please make that correction. We have this as a k minus 1. And we have to correct that. Thanks. So this is k minus 1. I have to correct it here as well. And what we have is the natural logarithm, and we will have a numerator and denominator. Okay? Javier, once again. What is the numerator?
A minus k1.
It's just first the constants. We are just evaluating this. What else?
Minus k
Minus 1
minus 1.
is 0. Denominator?
The k1 plus k
Minus 1 times is 0. We are evaluating for a0, and this is just a constant. Okay, so that is the integral. What do we have there? We can cancel terms because we have a positive and a negative term of a0. So this will be okay. So we will have that, and let me rewrite just to have this. So we have two terms in the numerator and one term left in the denominator, which is k1 times a0. And that is equal to minus k1 plus k minus 1 t. That is our linearized form for this model. Okay? But I will do the anti-logarithm. So we will have this, if you allow me to do this just in one step. So the anti-logarithm, I get rid of the logarithm there, and this is going to be an exponential term, e to the minus k1 plus k minus 1 times t. We have now terms to move. So first, I will move this, let me write it, be comprehensive here. And please do write this on your notes. So first I have this k1 times a0 multiplying the exponential term, k1 plus k minus 1, t.
It is k minus 1.
Minus 1. Sorry, I'm dropping the minus 1 while I'm writing. Yes?
I have a question. Why do you leave the k1 plus k minus 1 inside the integration if you already take it out?
I took it.
No, but it is inside the natural logarithm, but since...
No, we are not taking this out. We are just completing the variable. So the variable is the whole thing.
Okay.
Okay. the variable is the whole thing. So it's going to be always there. And it's important because that is going to be our rate constant here, our observable constant. It's interesting. We will discuss this further. No? And what else can I have? I can bring this, which is subtracting, which is just a constant depending on A0 here. So I will do that on the same equation. So this is
divided by Q1.
yes, that is a plus. Make sure that we are having our values.
Yeah, that will not be.
Yes. Sorry, I'm
Yes.
adding terms that should not be there. Actually, we can factorize. Let's factorize A0 and divide this over K1 plus K minus 1. And this will be just K minus 1 plus K1 times A0 e to the minus K1 plus K minus 1 times T. There we go. And that is our concentration of A function of time. Okay. Just for as a comparison, when we had A in a first order reaction decomposing, A was A0 e to the minus K1T. So now we have another term. Good. What is this equation telling me? We have to analyze first.
That just depends on the constant.
The reaction depends on the constants heavily. Whatever will happen depends on both constants. What is interesting, and you might really be surprised by this, is K1 and K minus 1 are adding up, although in the scheme that we have, these are going in opposite directions. So that is interesting. That means that reaction is going a little bit faster.
There is no concentration.
Ah, yes, of course. Thank you very much for noticing that, because it's factorized. It is factorized. Thanks. Yeah. Sorry.
So B is acting like a catalyst.
No. No, B is just following.
The reaction.
However A is changing, B is following. It's just doing the mirror stuff. What is that? Try to say it in English.
It's adding concentration of A, so it's like instead of the concentration of A decreasing, it's just
Getting stable to a point. Exactly. So what will happen? What will happen when we make this reaction go so long that time tends to infinite time? If t goes to infinite time, what will be A? Let's analyze that. So this is a constant, these are constants. Sorry, this K1 is multiplying this exponential. So here we have the time variable. What happens when we make t go to an infinite time? How much will be this number? Zero, exactly. And what am I going to be left with? What are the constants that will be left?
K minus 1.
Initial concentration.
Initial concentration over K1 plus K minus 1 times K minus 1.
So if I do the reaction for an infinite time, A won't be zero. That's what you were saying. It's not going to go drop to zero. What is going to be the concentration for B? That will be for B, and we are calling this B in an infinite time, so B infinity. That will be A0, which is this. We can factorize A0, and we will have 1 minus K minus 1 over K1 plus K minus 1, and this will be A0, K1 plus K minus 1 minus K minus 1 over K1 plus K minus 1. And we have this term, which is a negative, cancels this, and therefore B concentration at an infinite time will be K1 over K1 plus K minus 1 A0. Okay? So what are these concentrations? A infinity, B infinity. These are concentrations in the equilibrium. Exactly. So if I have an equilibrium, that means if this has reacted for such a long time that I'm reaching the equilibrium, my equilibrium constant should be concentration of B over concentration of A at that infinite time. And now if we bring these values here, this will be K1 over K1 plus K minus 1 A0 divided by K minus 1, K1 plus K minus 1 A0. And what I'm left with is K minus 1. Okay? So my equilibrium constant depends on the ratio of the two rate constants. Okay? So I think what is worth it here is to graph that. So I have 5 minutes to do a plot of what we have been discussing. And I'll try to do this. Now, what happens if K1 is larger than K minus 1? What do we expect? We will have preferentially B. No? So K1 is determining which of the two? K1 is determining. Okay? If this is, for example, let's say K1 is 5 times K minus 1, this means that the concentration of B at the equilibrium will be 5 times the concentration of A. So the rate constants will determine this. So let's try to make a quick plot. Hopefully we can finish it now. So I'm going to open a new plot, and we are just going to write an equation. Let's first write the equation for A. So I'm going to do plot. Let's assume A0 is 1. So I won't write the initial concentration, just it's going to be 1. So what I have to, before, let's call K minus 1, let's make it, we said 5 times larger. So K minus 1, let's make it 1. Oops, it's not going to. K minus 1, let's see, yeah. And K1, I will make it 5. So these are just some constants. So therefore, I'm going to, let's call it AX, so I can write it once, and probably I can change numbers. So this will be A0, I said 1. So AX will be A0 times K minus 1 plus K1 times exponential factor of minus K1 plus K minus 1. This is multiplied by time, which is our X, close parenthesis, divided over the sum of K1 and K minus 1.
Just that minus 1 over.
There we go. And I think, yeah, that should be fine. So now I do a plot of AX. Something is wrong.
It is the K1 plus K minus 1 is in the exponential.
Yes.
So it is
Let's see if I'm plotting this correctly. Plot. This should be limited to 1. Where's the mistake? Let me change two numbers. So we said K minus 1 is 1, K1 is 5. This will be 1 plus 5, 6. And this is divided over 6. Ah, yeah, there's a mistake here. Why is that?
The 1 plus
Yes.
5 wouldn't be in
No,
parentheses.
it's the scale. This is weird. I did not notice, but we were plotting in the negative scale or range. So this is from 0 to whatever positive value. Okay. Now, here we go.
Okay.
Yeah, that was the problem. Of course, this is allowing for, yeah, there we go. So I don't need to go too far away. So I will just plot to probably 5 or 10. No, 10 is too much. I will just plot to 5. We plot. Yeah, this is dropping so fast, but it's reaching. There we go. We plot. Now I can plot or replot 1 minus 8. There we go. So these will be the concentrations of A and B. So you see the ratio is, the initial concentration is 1 and it's going very fast and then reaching a point at which the concentration is not changing anymore.
Yes.
And the concentration here is almost 0.2. Meanwhile, this the concentration of B is going to almost 0.8. See? So probably when you were discussing equilibrium from the kinetic point of view, you were told that the equilibrium is reached when the rate at which A is consumed is equal to B that is transformed. This is not entirely true. Equilibrium is reached when these two are 0. So when do we have equilibrium? When we are here. So we're here. So as I move in time, what is the rate of the reaction? 0. The slope is 0. So equilibrium is when the rate is not the same. Because you see, here I have a rate that is the slope of this reaction and is the same for B. The rate of transformation of A and B is the same, but this is not equilibrium. Equilibrium is reached when we have reversible reactions, when the time is almost 5 times the sum of K1 plus K minus 1. So at less than 1, we have equilibrium. And you can see if this is 1 and this is 5, or the other way around, this equilibrium condition is reached at almost 1. And we see, and that's why we have a very fast reaction. Okay? If the cases are different, let's say 10 times or 2 times smaller, very quickly I will change K minus 1, let's make it 0.5 and K1 1. Now you can see this reaction is taking longer to reach equilibrium. And maybe for the 3 seconds that I'm plotting here, almost at the end of the 3 seconds is that where I'm reaching the equilibrium. Okay? So what happens is, if you have a reaction that you are analyzing, you know that A is producing products, and you are trying to fit this data to order 1, but something is missing, something is behaving strange. It might be the case that it's not a different order than 1. It might be the case that you have a reversible path. Okay? So that's why you have to have enough time to plot your data and make sure that your data is telling you that this is not changing anymore. So you do not confuse that with a second order, for example, or a third order. It's just reversible. Okay? So this is something that you have to investigate on your reaction. Okay? Good. We have the 2 sets of schemes left, and we will discuss this